Hey, welcome everybody. Coffee with Caleffi. Bob Hot Rod Rohr here, coming from Missouri. Jody, we've got with us today. He's our manager of engineering training for Caleffi, and he's up in Canada as we speak, and he's going to be doing the presentation from there. This is actually the second part of last month. He did it on combustion, and this is really takes it the next step where you design around high efficiency equipment. And Jody's done a great job with this. I've gone through it a couple times with him, and not only has he presented it in a really realistic but an understandable way, because we're trying to do this non-biased. We're not in the boiler industry, so this is a really good look at how you can design around condensing equipment. So great job, Jody. Take it away.
Yeah. Well, thanks for all for attending. Just so you know, I'm actually doing it up here in Winnipeg from our rep's office, Quipco Limited. I do have some people with me in here, so if you hear a little bit of background noise, it's the people moving around, and I have to thank them for showing up. It's always nice, and it's actually interesting to do it with a live audience, so we'll see how that works out during the course of the presentation. Now, the one thing that you will notice, as Bob and I had worked through this, I kind of had to trim this down a little bit. For me, a lot of times, the challenge is trying to just talk for 1 hour. So there are things on the condensing side that I really wanted to talk about that didn't make it into this presentation. I probably will do a part 2 somewhere in next year's rotation. But I hope I got the right information out there to give you really a feel for where we're going with it. Now, we start to look at condensing boilers, and I've worked for boiler manufacturers in the past, and I've also worked for rep firms. And when we look at a project going in, whether it's residential or it's commercial, there's always, as I refer to it, as the efficiency puzzle. There becomes expectations, and there's trying to drive the expectation. I look at that bubble in the center there, boiler efficiency. On the residential side, everybody talks about the AFUE, the annual fuel utilization efficiency. That number comes with the boiler. It's on a yellow sticker on the side. It gives the homeowner, the building owner, the installing contractor a certain level of expectations. I'm standing here in the office. I happen to be standing in front of a triangle tube, Prestige. I look at the side of it. It has an AFUE number of 95. Pretty much a standard throughout the industry. That's where most boiler manufacturers try to end up. Now, the reality is that boiler is not operating in a laboratory. It's operating within a building. So all of a sudden, when I look at the boiler efficiency and I try and bring it to a system efficiency, I have to really look at the system that it's working with. And I call it the installation constraints. I look at the installation. What's the scope of the work? Is it a brand new job where we're starting from scratch? I'm doing radiant. I can do everything I possibly can to be as efficient as possible. Or is it going to be a retrofit job where there's minimal amount of work? What's the budget? What's the material cost? How much labor is involved? Because when I start to look at the constraints of the installation, all of a sudden my expectations of performance change based on the constraints the installation puts on it. Then I hand it over to the building owner, the homeowner. All of a sudden, I have to account for their expectations, their desires. Are they really concerned about efficiency where they're looking for the best water temperature to maintain room temperature, or do they want to have the ability to bring the rooms up to 76 degrees Fahrenheit? I have to sacrifice some efficiencies for those kind of expectations. Are they asking for radiant heating, but they're really looking for floor warming? The one that always comes up in a lot of the retrofit is, are they looking for comfort? I've had people that I've done systems with, and they're like, I can't feel the heat. And it's like, are you comfortable? They're like, well, the house is 70, but I can't feel anything coming out of the radiators. Well, we have to make accommodations for these. And all of a sudden, when I start to make these kind of accommodations, I sacrifice a little bit of efficiency. So when I look at a project and I'm thinking about that efficiency side of things, it really becomes, how does the 3 circles align? Ideally, I'd like all 3 of them to align on top of each other, and I'm going to be in the neighborhood with that AFUE number. In reality, a lot of times the installation constraints and the building owner's desires result in the performance being a little bit less than the expectations going into the installation. Now, from the aspect to today's discussion, I want to talk about it as far as what can I do to maximize the performance of that condensing boiler. Here it is in a nutshell. We're going to see this here. You'll see it at the end as well. Okay? We're going to talk about the boiler ratings. You really have to understand what they mean, so when you're trying to achieve it, you know where there are the shortcomings in the actual application. We'll talk about proper sizing of the boiler. We'll talk about outdoor reset. And we'll keep coming back to this. For me, outdoor reset is a must with a condensing boiler. We'll talk about water temperature selection. That will affect efficiency. We'll talk about the differential. We'll talk about burner startup. And then we'll also talk about the one residentially that a lot of times never happens, about balancing the system. All of this plays into the performance of the system, and it really decides whether I'm running at 95% efficiency or 86% efficiency or somewhere in between. Now, from an efficiency rating, all boilers in the markets will have a couple of efficiencies associated with them. Residentially, and residential boilers are defined as any boiler less than 300,000 BTUs. It's going to have an AFUE, an annual fuel utilization efficiency test. It's also going to have a steady state test. That steady state is used to determine the boiler output. Commercially, commercial boilers are greater than 300,000 BTUs. It's going to have a combustion efficiency test, and it's also going to have a thermal efficiency test. Let's take a look at some of these tests. Where we're going to spend most of our time, I would say, is talking about the AFUE. A lot more residential boilers sold than commercial boilers. AFUE, annual fuel utilization efficiency. Okay, if I look at the box on the bottom, that's the standard for the test, ANSI ASHRAE Standard 103. Okay? Now, the thing with this test is it's not just based on test data. The annual fuel utilization efficiency is a calculated value to represent the annual seasonal energy usage of a boiler. Okay, so when we start to look at it, you have to realize that is the requirement, not that it's just a test number. So let's talk about how it's performed. Okay, the boiler's put into a test condition. It's a constant load, constant water temperature. So we hook it up to a constant load. Adjustments are made until it's steadied out at 120-degree water going to the boiler, 140-degree water returning. The information that we're interested in, okay? How much condensate is coming out of the boiler? The condensate will tell me how much of the latent heat I'm picking up. And then I need to know what the air temperature is in the room. I want to know the O2. The O2 will tell me about excess air. And then I also want my flue gas temperature. So with the O2, the flue gas, and the air temperature, I can look at my sensible losses. Here I can look at my latent gains, and then I run it through the program, and I come up with an AFUE number. I would say if you look at the bulk of the boilers out there, every manufacturer is going to have a handful of boilers that are in that 95% AFUE number. Now, question always comes, how close can I get there, or where are some of the shortcomings when I look at actual application to compare to it? First, I'm going to start off at the middle about those temperatures. 120 going to the boiler, 140 coming back. Okay? If I'm running at any other temperatures, I'll deviate from the AFUE. So if I'm running at 130 coming back to the boiler, or 150, higher water temperature, my efficiency is going to be lower. Conversely, if I can drop my water temperatures, I hook it up to a radiant system, 190 coming back to the boiler, 110 going out to the system, I'm going to run better than the AFUE number. So that's going to affect how the installed performance of the boiler is going to be seen. Other things, okay? I'm measuring O2. I'm kind of an old school guy where I generally talk about combustion in terms of CO2. And I think if you look at most boiler manufacturers, CO2 tends to be where they have their information on the boiler, okay? So the test doesn't specify the O2 or the CO2, which reflects the excess air. It just has to be within the range of operation for that boiler. So if I don't set my burner up and run the burner similar to how they're doing the AFUE test, I'm going to have some losses. I'm going to not run as efficiently as they are. So if the manufacturer says the range of operation is minimum CO2 is 8.5, maximum CO2 is 10, if I'm running more towards the 8 or the 8.5 number, my performance isn't going to be as good as the test if they're running that test somewhere around that 10 number. So combustion setup plays a factor in how well that boiler performs. Okay. Now, the last thing I want to talk about in here is the conditioning of the space. Okay. When the test is run, the space is heated and humidified. I can bring the temperature in that space up to 90 degrees Fahrenheit, and I can bring the relative humidity up to 85%. Since I'm up here in Canada, I'm going to talk about the metric system. Okay. By the way, it also works easier for these littler numbers. So if I look at that relative humidity and temperature, that represents 25.5 grams of water vapor per kilogram of air that's coming into the boiler. Think about that as free condensate. So with that amount of moisture in there, I gather up that condensate and it helps the efficiency numbers. If I am doing a sealed combustion boiler, I'm bringing air from the outside, and that air's dew point is 0 degrees Celsius, 32 degrees Fahrenheit. That moisture content drops down to 5 grams per kilogram. So one of the things that you have to recognize is because of this testing protocol, there will be deviations between the delivered performance and the AFUE number if you're looking at it as a snapshot in time for the efficiency. Okay? So this is the AFUE test. On the internet, there's a great amount of information. I've pulled information from a lot of different boiler manufacturers. This happens to be for the night boiler. Okay? And where I see that blue area, there's that blue arrow, there's my AFUE numbers. So from an AFUE standpoint, most of these boilers are running at 95% efficiency. Now, we also talked about doing a steady state test. If you look at what I have circled in blue, here's the heating capacity. So if I look at that smallest boiler, the heating capacity here is 51,000 BTUs, the input is 55. If I do my math, divide the output by the input, multiply it by 100, it's coming out to 92.7. You notice this number does not reflect the AFUE. Different tests, different procedure, different number. Okay? This steady state efficiency, this heating capacity, or you'll also hear it referred to as the DOE heating capacity, normally is one of the pieces of information used to size the boiler. So same boiler, different tests, different results. When I go to commercial, I'm going to kind of go the short version of the commercial side. Commercially, I have 2 tests, thermal efficiency and combustion efficiency. The test that they're run out off of is something called BTS 2000. So these are also a steady state, constant water temperature test. Thermal efficiency looks at the water side of the boiler. So we'll measure the energy going into the boiler. We'll gather the hot water coming out of that boiler, calculate the BTUs that's deposited in that water, compare it to the input, and get an efficiency. The combustion efficiency looks at the fire side. So it's very similar to that AFUE. It's about sensible losses. I need to know stack temperature. I need to know ambient. I need to know my O2 or my CO2 level. And then I have to gather my condensate to calculate the latent gains. Every commercial boiler will have them. They're going to look something like this. This happens to be out of a Baderis Tech Data Manual. And you'll notice the 2 numbers do not match. You'll find if you look through, sometimes they will match, but more often than not, they don't match because of the differences between the 2 tests. Okay? Now, I also want to look at this information over here for a specific size. So if I look at that red block, you'll notice there's an input, there's a gross output. There's a gross output at 104 degree water supply with an 86 degree return. There's also a gross output at 176 with a 140. So the gross output is 5 million BTUs. At 104, it's 5.3. At 176, it's 4.8. Somebody has to size the boiler for the application. Because the rating, the gross output of that boiler changes with water temperature, most of your manufacturers will give you a series of choices based on the water temperature, so you select the right boiler for the right application. Okay. The other thing that you'll find in a lot of manuals that I think is nice, actually going back to Lochinvar, looking at CREST, efficiency charts. So the efficiency charts, the vertical axis is about efficiency, the horizontal axis, return water temperature at a 20-degree Fahrenheit rise. And then the curves off of there are at various firing rates. For this discussion, I'm going to look at it from the aspect of 50% input. So I can look at this and say, you know what, if I put this boiler in and I have a return water temperature of 120 degrees on a 20-degree rise, the boiler is going to operate at 90% efficiency. If I drop the water temperature down from 120 return down to 100-degree return, the 90% efficiency jumps up to 94. So one of the reoccurring themes that you'll hear for the rest of the hour is I want to push the water temperature down as physically as low as possible. The lower the water temperature, the higher the efficiency. Okay.
Hey, Jody, on that slide, and there's a good question that came in, and when people are using condensing boilers for domestic hot water generation, how do you deal with the mixing valve required temperature differential, limiting how low you can set that temperature and, of course, how much it can condense? So if we want that spread on the differential for the mixing valve to be operative, obviously we've got to run that boiler temperature up high enough to have that differential. So
I think probably, I think from the time constraints, we probably will save that for the written part of the responses.
Okay.
You know, 'cause I think that's probably about a 5-minute. For the guys in the room, they were asking about domestic hot water. So I think we're going to save that and use that as one of the answers that we'll do as a written, because I think it's going to be a longer discussion that we might have time for during the course of this. All right, Bob?
All right. Well, how about a yes or no one then? He said, are you saying that the efficiency ratings are done based on an 85% ambient relative humidity, which is unrealistic for winter conditions? Just going back a couple slides on that test.
The answer is yes.
Okay.
So, you know, so if you typically look at the test, I'm going to jump back there. Typically, the test is run under those conditions.
The box.
The box. And the answer is absolutely, they do not reflect reality, but think of it as consistency. If every boiler is tested under the exact same conditions, the numbers will give you differentiation between the different boilers under the same conditions.
Right.
Okay.
Thanks.
You're welcome. So the boiler has a specific efficiency associated with it. I have to choose the best boiler, okay? And I'm actually, I gotta go to a quote to you know, one of the friends in the industry. The other day I was looking through Mechanical Hub, and one of the friends of the industry, his name's some of you may know him, Bob O'Brien, and Bob lives out on the Isle of Long. If you actually look at it on the map, the rest of us know it as Long Island. But Bob had put this article in Mechanical Hub, and it was about sizing boilers for indirect water heaters. And I liked Bob's quote. I'm actually thinking it should either go on a T-shirt or on the wall at anybody in our industry that is doing boiler sizing. And his quote, where his quote says is, whenever boiling size is in question, oversizing is never the right answer. I love that. I want to have that on the wall of my office. But when we start to look at sizing a boiler, you know, there's a lot of different methods to go in there, and I see a lot of these different methods, particularly when somebody is replacing the boiler. You know, I'm like a lot of guys, I get into and check a lot of the boards and discussion groups on the internet about hydronic heating and heating in general. And a couple that come up that I'm not a big fan of is either the direct swap out method or the measuring existing radiation. I use my house as an example. Okay, in my house when I moved in there, I had my boiler was a atmospheric cast iron. The boiler's output was 91,000 BTUs. By the way, as a reference point, the house was less than 1,500 square feet. Okay, at the time I had worked for a rep firm. I did design. I had RightSoft software to do heat loads on my computer. So with RightSoft, the biggest load I could find from my building was 40,000 BTUs. So if I would have done a direct swap on that boiler, I was replacing the boiler with replacing the boiler that was over twice the size with another boiler that was over twice the size. You know, the same thing with measuring the heat emitters. Probably a little bit better, but with both of these methods, it always is up to you're relying on somebody that may have done it 15, 20 years ago, relying on them doing it right. You know, really, the best method is really to go in there and do a heat load on the building, figure out the actual load of the building, and size the boiler for that load. You know, a couple of other manufacturers do have other various methods, but for me, it's the building does have to be analyzed to make sure that I'm doing my boiler sizing right. Okay. Now, why is everybody adamant about not oversizing the boiler? Okay, it's all about cycling. Okay, the boiler modulates. It has a turn down ratio. Pretty much the standard in the industry, I'd say, is a 5-to-1 turn down ratio. With a 5-to-1 turn down ratio, the minimum fire on the boiler is going to be about 20% of the input. It's about the mild days. If the boiler output is greater than the heat load of the building, how things stay in balance is the boiler has to cycle. Now, one of my cycling losses, it's all about the operation of the burner. When a boiler goes to fire, the burner doesn't light off the first second the call happens. The boiler has to go through a pre-purge. And then that pre-purge, it has to move about 1.5 times the combustion chamber volume to evacuate the chamber of anything that's in there. Particularly, you know, usually people look at leftover gases from the previous combustion cycle. Now, residentially, small chamber, that's probably not a long pre-purge. But I get into commercial boilers, 15, 20, 30, 40 seconds of pre-purge. The thing with heat transfer is a two-way street. It's all about hot and cold. It's not one directional. So if the heat exchanger, the water in that heat exchanger is at a higher temperature than the combustion air coming in, boiler sitting there at 120 degrees, I'm bringing 30-degree air into the boiler. That 30-degree air will extract heat from my boiler and just dump it outside the building. Essentially, from my system efficiency, I'm lowering the efficiency of my system during this pre-purge cycle. So from the aspect of performance, I like to reduce the cycling of the boilers on these marginal temperature days. When does it happen? Well, I'm going to come back to the market that I worked out of. You know, very familiar with the Boston area. I used to design for 0 degrees. If you're interested, I was one of those guys that designed for 99.8% of the heating season. I didn't want to get cut short. So let's say I'm designing for 0-degree day. Let's say I'm designing around a 70-degree inside air temperature. And for the sake of the argument, I'm going to take wind out of the picture. We're just going to look at the heat transfer changing based on the temperature difference from the inside to the outside. If I right-size the boiler is exactly sized for the operation. On a 0-degree day, I need the full output of the boiler. It's running at 100%. As the outside temperature goes up, the boiler goes down in its modulation. Eventually, it gets down to the point where I'm at the lower end, that 20% number, and as the temperature gets higher, the boiler has to cycle to keep up. With the right-sized boiler under those conditions, that happens on a 56-degree Fahrenheit day. 56 and lower, I can match. 56 and higher, I have to cycle. That's with a right size. I increase it, I oversize by 33%. The 56-degree day becomes a 51-degree day. 100% oversize. It now becomes a 42-degree day. So all of a sudden, if I'm not right-sizing my boiler, putting the right boiler sizing for the application, I increase my cycling losses, and my system isn't as efficient as it needs to be. Now, let's talk about a couple of the ways I can address the cycling. First, let's take a look at a multiple boiler installation. I have a drawing out of one of my Hydronics. let's talk about a 3-boiler set. So commercial building, 3 boilers. And the discussion with the designers that are pulling this together, I've had it often in the past, how are you going to size those boilers? Some of the guys will say, you know what, each boiler size for 100% of the load. Now when I have multiple boilers, I have my boiler turned down, but I have my system turned down. They're not necessarily, they could be the same, but not necessarily. So if I size for 100% of the load, any one boiler can carry the load on the design day. So all of a sudden, if my boiler has a 5-to-1 turn down, if I only need that one single boiler, my system turn down ratio is 5-to-1. I really haven't gained anything from the cycling side. Let's say I downsize my boilers, so all of a sudden each boiler now can only carry 75% of the load. On the design day, I now need 2 boilers, and those 2 boilers are running at 2/3 of their input. All of a sudden, I can start looking at combining the turn-down ratio to give me a better turn-down ratio. Under those conditions, the system turn-down ratio represents about 1.5 times any one boiler's turn-down ratio. So my 5-to-1 now becomes a 7.5-to-1. Okay. Let's drop it down to 50%. You know, at the 50% number, I have 3 boilers. I still have my redundancy. If I lose any one boiler, I still can carry 100% of the load. Because I need 2 boilers to carry me on the design day, my turn-down ratio is now twice any one individual boiler, which gives me a turn-down ratio of 10-to-1. I've shortened the course of the season when the boilers are, in fact, cycling because the load is less than the minimum firing rate of the boiler. So something to consider when you're designing around multiple boilers. If I'm doing a single boiler, buffer tanks can help. If you're interested, in Hydronic 17, it's about buffer tanks. There's great information in there about it. Additionally, earlier this year, John Siegenthaler did do a buffer tank coffee with Caleffi. Highly recommend you go back into the archive and take a look at it. It has a lot of great information. Now, with this buffer tank, the buffer tank doesn't address the turn-down ratio of the boiler. But what it does is it changes the balance point between the boiler and the system. I put that buffer tank in there. When the boiler is firing, it's satisfying the load in the building, but it's also storing thermal energy in the buffer tank. So I'm now extending the on cycle because essentially the boiler has a bigger load. Okay? Eventually, the temperature could be on the boiler, could be controlled off of the buffer tank. It's satisfied, the boiler shuts down. Now what happens is the system's load is now drawing energy out of that buffer tank, and I'm extending the off cycles. So I put that buffer tank in there. I'm still working off of the boiler's turn-down ratio, but have essentially reduced the cycling by extending the on cycles and extending the off cycles as well. So from the boiler cycling side of things, a couple of points. You know, we talked about these already. Don't oversize. In a multi-boiler application, let's go with the smallest boiler possible. And also, if I'm doing a single boiler and I want to reduce my cycles, consider using a buffer tank to extend the off and on cycles. Okay. From this point forward, it's all about maximizing the condensing. Okay. So if I'm designing for maximum performance, you know, part of my combustion process is I produce water vapor. So if I'm trying to maximize the performance of a condensing boiler, what I have to do is I have to increase my latent heat gains. I have to also decrease my sensible heat gains. So I got to get water. I got to get my condensate out of the boiler. I have to get the boiler to condense and the water to come out, releasing energy. And I also want to reduce my sensible heat gains, my stack temperatures. You know, non-condensing boilers, I usually look at stack temperatures 300, 400, maybe 500 degrees Fahrenheit. When I look at a condensing boiler, my expectation is the stack temperature is well below 200 degrees Fahrenheit. So I'm pulling back a lot of that sensible heat that would have gone up the chimney. Okay. Now, round figures, and I'm actually going to just go kind of in the box in the center there. round figures, when I start to look at the condensing boiler's efficiency, if somebody asks me how efficient is that boiler, my answer is always look at the condensate drain. How much water is coming out of there? Because for every gallon of condensate that comes out of that drain, that's about 8,000 BTUs of latent heat that I've recovered. Okay? So I have to get that boiler to condense. I have to pull that water vapor out of the combustion process, and that's what's really going to give me that higher efficiency. Okay? Now, combustion is important. That's actually why we talked about it last month. Okay? When you start to talk about combustion and you start to talk about dew point, one of the things I run across a lot is the thought of the dew point for natural gas is a spot frozen in time. Dew point is 135 degrees Fahrenheit. The answer is it's a 135 Fahrenheit sometimes. Dew point is really based on the amount of water in the water vapor in the air. You know, back in the beginning, talking about kilograms of water vapor per, grams of water vapor per kilogram of air. It's about the combustion process. So when I look at combustion, I can make adjustments. You know, a manufacturer may say that the boiler should be somewhere between 8% CO2 and 10% CO2, or 8.8 to 10.2. Every manufacturer is going to have something in that range. The CO2 level, or the O2, is a description of how much excess air is coming into that combustion process. Round figures is, so if I'm running at about 10% CO2 with gas-fired equipment, natural gas-fired, I'm probably running at about 20% excess air. The more excess air, from a combustion standpoint, I always get a fixed amount of water vapor from my combustion process. If I burn a therm of natural gas, I'm going to get about 9.3 pounds of water vapor. Okay? So if I add excess air, that water vapor becomes a smaller portion of the entire amount of combustion gases in the combustion chamber, and it becomes more difficult to get that boiler to condense. So what happens is, as I change the CO2 level, the dew point changes as well. So if I go in there and I set my CO2 at 10%, my dew point's at about 132 degrees Fahrenheit. If my CO2 is set at 8%, my dew point's about 122. Now, why I chose those 2 points are those 2 points represent where most of your boiler manufacturers set the ends of their range of combustion, usually somewhere around 8 to somewhere around 10. So I can take 2 boilers from the same manufacturer, set one up at 8% CO2, set one up at 10% CO2, and the performance is going to be different. And the only difference is the burner setup. Okay? So when I start to look at setup, that burner setup is real key to that condensing boiler. Because with this dew point temperature, the efficiency, the boiler doesn't start to condense until the water temperature drops below there. So if I can run with a higher CO2 that gives me a higher dew point, then the boiler condenses earlier and the boiler condenses more for any given water temperature, and my delivered efficiency is higher.
Jody?
Yes.
What's the practical implication for all of our listeners up in areas that don't have natural gas but are running boilers on propane? What's the implications of this curve for the propane fired boilers?
I actually don't have a curve for the propane. For the guys in the room, the question was, how does propane reflect this? Okay? Propane, the curve is going to be very similar. The numbers are probably going to be a little bit lower, because if I look at natural gas, I'm looking at about 10% of the energy tied up in the water vapor. I want to say propane, I'm somewhere, I think, around 7% of the energy tied up in propane. So with propane, I get less water vapor per unit of energy than I do with natural gas, which is going to put the numbers down slightly lower than what we're looking at here.
Very good, thanks.
Okay. So from the aspect of setup, if I'm trying to maximize condensing boiler performance, I have to set up the burner. Okay. Now, most of your condensing boilers from the manufacturers will come pre-set up by the manufacturer. Okay. It will be somewhere in the range that's acceptable, 8 to 10 or 8.8 to 10.5, whatever that manufacturer specifies. But if I want to maximize the performance, I'm probably going to want to be around at least 9.5 on CO2. 9.5 will give me a dew point in that 130 degrees Fahrenheit range, which will help me generate good performance as a condensing boiler. Now, once the boiler is set up, then it's all about what do I do with the water temperature. Now, if I choose 130, if I look at that 130 number, that's where condensing starts to happen. And if you look at this chart, that number generally means I'm running at about 87% efficient. Okay, so if I take a boiler, if I take an installation, particularly a retrofit where they have baseboard and they're thinking, I need to run 180 going out, 160 coming back at 160, I'm running at about 86% efficient. If I want to push the efficiency, I need to drop the temperature. So if I drop it from 160 down to 120, all of a sudden I'm looking at 90% efficiency. Okay. Now, from the aspect of the system, lower water temperature equates to better efficiency. Am I low, am I medium, or am I high as far as my water temperature? Am I doing radiant? Am I doing some form of radiator? Or am I doing baseboard? Now, the reality is, everybody thinks about baseboard as being a high temperature system. My answer always to the guys are you sure? Because if I look at information being provided by baseboard manufacturers, you know, baseboard is, here referred to a lot as baseboard radiation, but it's actually a convector. Air comes in, passes over the fins, it exits. And this will generate a convection current that will turn the air over in the house, keeping that house warm. Typically, you ask somebody about baseboard, and they say, okay, the baseboard's going to put out 600 BTUs per linear foot. They're thinking it's 180 degrees. This chart is one of the slant fin charts. You know, again, another great website with great information. There's 180. At 150, I can get 400 BTUs per linear foot. At 110 degrees, I can get 160 BTUs per linear foot. So the key point is with baseboard, it's not that the baseboard stops performing when my temperature drops down. It's just that the performance drops off. But if the performance drops off, I can either increase the baseboard to get the performance back up, or utilize this fact by running off of outdoor reset to balance the building to the heat load that's occurring in that building. So a lot of guys will look at this and say, you know what? I can't use baseboard. This is what I need. I mean, I can't use a condensing boiler. This is what I need. I got baseboard. I need to run hot. I need to run 180 degree water. And my answer is, at 180 degree water, you know, that condensing boiler is probably not doing you a whole lot of good. You're probably running at about 86% efficient. But then it's, well, why don't we do outdoor reset? Let's run at 180 degrees on my design day. And by the way, we're back in Boston, Massachusetts again. You guys might have figured out where I came from. And on the design day, I have that 180. But now let's start dropping that water temperature as the outside temperature gets milder. And if I choose the exact right curve, that water temperature will always give me the right heat into the building to stay balanced with the heat that the building is losing. Now, my burner is set up at 9.5 CO2. There's my 130 degree dew point line. You notice at a certain point, the supply water temperature all of a sudden drops below the dew point. With condensing boilers, I'm concerned about the supply water temperature, but I'm more interested in the return water temperature. Okay, here's my return water temperature. Here's where the return water temperature drops below the dew point and the boiler starts to condense. If you're wondering about what that number is, that number is a 20 degrees Fahrenheit day. So when the temperature is less than 20 degrees Fahrenheit, the boiler's running in a non-condensing mode. When the temperature is, outside temperature is higher than 20 degrees Fahrenheit, the boiler will be condensing. Let's overlay hours or percentage, ASHRAE data for Boston, Massachusetts. Okay, so each one of these columns represent, and I'm going to go with the percentage of the heating season were between 68 and 54, or 54 and 41, or 41 and 28. Look where my crossover point is at 20 degrees Fahrenheit. It's right smack in the middle of the column that represents 10% of the heating season. My 14 to 0, that's 2% of the heating season. My 0 to minus 13 Fahrenheit, that's 0.2. So I can put this condensing boiler in on the design day. The boiler is not condensing, but if I look at this, greater than 90% of the heating season, that boiler is going to be condensing. So I still have good performance. And where are those performance numbers? I'm going to revisit a couple of points we dropped into along the way. This point right here, 120 degrees Fahrenheit. That's where the boiler crosses over to 90% efficient. So that boiler is going to be 90% efficient for about 88% of the heating season. Here's another point, 100 degrees Fahrenheit. That represents 94% efficiency. And again, it's going to be better, 94 or better, for greater than 50% of the heating season. So if I do it right with a condensing boiler, I may have to drive a higher temperature on the design day, but the end result is if I look at my seasonal delivered efficiency, it's going to be greater than 90%, and I'm going to save that homeowner some fuel. Now, do I need 180 degree water? Can I get by at 160? 160 means I probably have about 18% extra radiation in that house. The way most market-sized baseboard, that 18% probably exists. You know, I need a 7-footer. I put in an 8-footer. You know, that baseboard is there. If I can get by at 160 going out and 140 coming back, that crossover point is now 11 degrees Fahrenheit. So anytime the temperature is above 11 degrees Fahrenheit, the boiler's in a condensing mode. Okay. There's my 90% point. There's my 94% point. Okay. Another thing I wanted to point out here, you see that 7 degrees there? That 7 degree number right there represents 99% of the heating season. That's my ASHRAE 99% coverage temperature for Boston, Mass. No. Yeah, I had a conversation going here in Winnipeg. Your number is going to be slightly different, but the numbers are probably going to be, if you start looking at the overall, it's going to be fairly close. Okay. Now, the reality of baseboard. Baseboard doesn't perform well when I'm down around 80, 85, 86 degrees. So I can't reset all the way down to the bottom of this true heating curve. I'm going to have to tie it to a temperature. For our discussion, I'm going to tie it to that temperature there that's circled at 104. You know, at 104 degrees, 110 degrees, 100 degree, the baseboard still will perform adequately under those conditions. So I have to be able to maintain temperature at that baseboard to maintain comfort in the house. Couple of ways of doing it. What I can do is I can tie the endpoints with some of the outdoor reset controls out there. I can tie the endpoints to specific temperatures, 65 degrees and 105, 0 degrees and 180. And then the boiler will modulate through those 2 points. The other thing that I can do is I can set a minimum water set point. Okay? I set that minimum water set point, all of a sudden the boiler flatlines at that temperature. So it'll reset down till it gets there, and when it gets to that point, it flatlines, and that becomes the minimum water temperature. This becomes my heating curve. Okay? And it allows me to do outdoor reset, but it also allows me to maintain comfort in the house by not allowing that water temperature to get down to too cold. If I was given the choice between the two, my choice is to choose the green curve. The area inside that triangle is lost efficiency. Because there'll be times on the yellow line where I could be running at a lower temperature, and again, lower temperature represents boiler efficiency. But the thing is, the boiler has to have the ability to do this. Okay. Now, the other thing that happens, the building has to be properly zoned. Okay. If that true reset curve truly is the right curve for the building can be running constant circulation, and it runs 24 hours a day. The zones stay open the entire time. On the yellow curve and on the minimum water temperature side of the curve, with those two curves, I'm always going to put more energy into the building than the building is losing. Okay? So in order to maintain comfort in the building, I have to make sure my building is properly zoned so that I don't overheat the occupants. Again, we always talk about efficiency, but always the overriding factor is going to be the comfort of the occupants of that building. Okay. So when I select water temperatures, my thought is, how low can I go? From an efficiency standpoint, definitely outdoor radiant is the best match. It's going to give me that lowest water temperature. But when I start to look at baseboard systems, and some markets that the retrofit work represents 80–85% of the boiler business is out there, retrofit is a way of life. It's got to be outdoor reset. Then I have to look at the job. Was there oversizing in the installation? If the boiler was oversized and the baseboard was oversized, it gives me the opportunity to drop the water temperatures down. Was the building envelope improved? Was the baseboard put in 20 years ago, but since then the building's been wrapped, it's been sided, triple pane windows, new doors, everything to improve the building envelope. All of a sudden something like that happens, the baseboard's oversized, the opportunity to drop the water temperature down lower occurs as well. Okay. If I'm concerned about the baseboard being marginal and they have dummy baseboard, is there money in the budget to put some baseboard under the dummy baseboard? Putting element under there, I can drop the water temperatures down again. And again, the lower I push the water temperature, the better the performance for a condensing side of things are. But remember, okay, with baseboard there's a performance limit, and that limit's going to be probably somewhere in the 100 to 110 degree range. So we talked about lowering the water temperature. Okay. Now, the other thing that we have to consider is my delta T, or my differential temperature. Historically in North America, we always design around a 20 degree Fahrenheit temperature. So if the water is going out at 150 degrees, the return water to the boiler is coming back at 130. So if I'm going out at 150, coming back at 130, my efficiency is 87%. Okay. What if I can open that differential or that delta T up? I don't operate off of a 20 degree delta T. I lower it down, I get to a 30 degree delta T. All of a sudden, my return water temperature is now not 130, it's 120. And with that 120 temperature, my boiler efficiency rose up from 87% to 90%. So when we start to look at applications, one of the things that has to be considered, particularly in new construction, is how wide can I make that delta T? Because with that wider delta T, I can get a much better efficiency. Okay. Other things to consider, not on here, but pushing the high delta T, I go with a high delta T. I need less water flow. I can get into smaller pipes, and I can go with smaller pumps as well to get the same performance numbers. Now, something that you do have to be concerned with, okay, and this changes from boiler to boiler. Okay, depending on the heat exchanger design, some of the boilers will have a maximum differential temperature across the boiler from supply to return where you can't exceed because they're worried about thermal stress on the boiler. So when you start to look at, usually if you stay within about 30, 35 degrees, you're covered. But if you want to say, you know what, let's push it up to 50, which occasionally happens, then you have to start thinking about the thermal stress on that boiler. So it is one of the points to consider. The other point, I'm going to come back to my series loops and baseboard. Okay? If I'm going out at 180 and coming back at 160, the performance difference between that first foot of baseboard and the last foot of baseboard is not that dramatic. But if I try and open it up to a 30-degree delta T, the first foot of baseboard, 600 BTUs per linear foot, last foot of baseboard, 400 BTUs per linear foot. And if that run of baseboard is divided up into 3 individual rooms, you will see a temperature difference in that room from the first room to the last room, unless the lower temperature is accommodated by adding in more baseboard. So generally, when we start to look at opening up the differential, I would say most of the times it comes off of the board as an option when I'm doing retrofit work with existing systems. But from a new construction side, definitely something to consider. Okay. Now, final point is balancing. And this actually is probably where I see a lot of jobs falling down. Everybody says, you know what, I've designed for 20-degree delta T. The job goes in, you look at the numbers, the performance numbers, the checking of it, that 20-degree delta T is always probably a 10, sometimes even less. Why is it? The installation went in, and this is more residential than commercial. Commercial is normally you have the certified balancer going in and setting up, but I'll see jobs go in there. You walk into the mechanical room, there's a bank of, let's go with 5 Taco 007s on the wall. Not a single balancing valve in there. You say, what are you designing for? It's like, oh, we got a 20-degree delta T. I'm like, really? Every pump has a 007 without a single valve moved to try and balance that system out. Typically, systems are over-pumped, not under-pumped. So if I don't use balancing valves to drive my performance, I start to drive the return water temperature up. When the return water temperature comes up, higher water temperature, lower efficiency. So I may think the green is my supply. I may think I'm designing, in my heart of hearts, I'm designing for this 20-degree drop in the system, but because I didn't put accommodations to balance the system, and I didn't balance it, in actual installation, I end up with this 10-degree delta T. That's the blue line. Higher water temperature, less time spent condensing during the course of the heating season. Ultimately, the efficiency of that system drops off. So, when we start to get to the actual, where the rubber hits the road, the balancing definitely is something that has to happen if I expect to drive the efficiency. It's like setting up the burner. It has to happen to drive the system efficiency. So if I'm looking at it from the aspect of efficiency, back to our list there. These are the things that I need to do, okay? First off, I really have to understand what that number means, because I have to understand whether it's an achievable number or for my application is realistically 91, maybe 92, a more achievable number, okay? I have to make sure the boiler size for the application. Outdoor reset is a must. I won't hit a high efficiency without it. I have to choose the lowest water temperature. I have to choose the largest differential that's applicable and suitable for that application. I have to properly set up the burner. I say this is one that many jobs out there, it never gets done. The boiler's preset by the burner's preset by the manufacturer. It goes on, it gets fired, we walk away. I've run across in the past from the different companies I work for. I'd worked with a lot of startup techs, and my conversation always was, hey, you came back from the startup. I'm curious, we pre-fired the burner. I had worked for a boiler manufacturer at the time. Did you make adjustments? And their answers were always yes. And I'm like, you adjusted it? What was it, below 8 or above 10? And like, neither. It was at 8.5. I'm like, you're fully within that range. And the answer is yes, but I wanted it at 9.5. So the techs that are in the know, I see them out there making this kind of adjustment. And from these techs are actually where I got my number of 9.5. It was their target. Okay? And then finally, I have to make sure I balance the system flow to ensure that the delta T, the differential temperature that I'm designing for, is the delivered differential temperature. I do all these, I can maximize the performance. You know, I can, on some applications, get up to the mid-90s. Most applications get up to at least the low 90s as the delivered efficiency during the course of the year.
I think, Jody, if you don't have anything else, I want to thank everybody for attending today, and we'll see you again in a month, and have a good day.
Thank you, guys.